Hello and welcome. My name is Michael.
My name is Kapoor, and today our video we're going to be showing you a little bit about how to calculate pi, some convergence series, the Chudnovsky algorithm, and some other ways of finding out how to get that 3.14.
That sounds amazing, Kapoor. But I have a question for you. What does pi mean to you?
Pi to me. I'm thinking of Thanksgiving pie, you know, yummy in my tummy pie.
Oh, Kapoor, you're funny girl. You know, our professor Erin McNicholas would like us to do possibly one day do a cooking video on, you know, a Thanksgiving pie. However, I think she's thinking more of the mathematical pi when it comes to a diameter of the circle and its ratio to the circumference.
That pie.
That pie, yeah, exactly.
Oh, okay, my bad. I'm, you know, hungry over here. That pie, we learned a lot in high school, and we learned the different formulas of how to find that pi, and we can use that symbol for everything, a lot of things, basically, and we just take that for granted. It's pretty powerful stuff. But Michael, what do you think when I say pi?
You know, I like pumpkin, but moreover, I think pi it's really powerful when it's used today in its extremity of being irrational. It's pretty spectacular, making note of how many mathematicians have gotten their hands dirty trying to figure out what pi is and how it represented and numerically how you represent pi. Everything from Chinese mathematics use geometric processes to get their whopping 7-digit approximation way back in the 2020 after era. The first accurate representation of the infinite series started with Leibniz in the 1600s, which we will talk about soon in our video. Seeing the growth of the accuracy is pretty incredible, and to think about how simple of a concept of the ratio of the circumference of the diameter can be thought of as irrational and infinite.
That's a very interesting way of thinking about pi, Michael. But for me, you know a better way of thinking of that is pi with Cool Whip.
Haha, that's a good one because it's cool. I got you. And so, the rest of our video, we're going to be talking about how to calculate pi, so let's get to it. Done. Throughout time, all the way from the Babylonians to today, people are trying to calculate the digits of pi. The current record is about 2.7 trillion digits. But how accurate were the mathematicians and the civilizations in the past accurate when they're representing pi? Let's take a look. Whoa-wee! That was a lot, and it was just the pre-20th century findings. As you can see, there's a lot of mathematicians. A lot of mathematicians attempting to find the accurate representation of pi. Pretty incredible to see such an accuracy done in the past. Now we're going to see, in the future, what it's going to look like beyond 20th century mathematicians to see how far they can get past 707. Dun dun dun! So now I'm going to talk to you a little bit about the infinite series that converges to pi, and how in the past how mathematicians were able to use infinite series to basically approximate and find decimals of pi. Way back then in the 1660s, they didn't have the ability to calculate their infinite series long enough to get so many decimal places, so this was the best I can as a kind of conceptual way to represent pi in a certain way. So for example, one of our mathematicians is William Broker. He's from England, and he was one of the first people to kind of figure out the lengths of the parabola and the cycloid, and he was also working off of works from Archimedes' quadrature of the parabola. So he kind of had the concept of being able to describe curves with different polygons and so forth. Additionally, he was also the first European to solve the Pell equation in number theory of that polynomial kind of concept. So that's kind of a cool concept as well. And so then he was also really focused on the idea of continuous fractions. And so he was able to take his knowledge of curves and ability to use continuous fraction to make this equation with pi over 4. So we have pi over 4, which equals 1 over 2 plus the previous one squared over 2 plus the odd squared. Same thing with 2 plus 5 squared. Over that we have 2 plus 7 squared. Over that we have 2 plus 9 squared. And over that 9 squared we have 2 plus 11 squared. And over that 11 just keeps going on to the odds. And so this is basically his way to represent the continuous fraction of pi over 4. If you want to make it more simpler, you can multiply each side by 4, and this whole thing by 4, to then basically that would change this numerator instead of 1 to be 4 instead. So that would be kind of a simple way if you were just to solve for solve for pi instead of solving for pi over 4. And so to make it more about solving for pi, then you would just make this more simpler, and that would be the way to go. He also was influenced by Leibniz when his convergence concepts, such as the idea of this kind of continuous fraction of 1 over 1 plus 1 squared over 2 plus 3 squared over 2, like that. And so that would equal 13 over 15. And then actually is going to come up to something that's going to be similar to our next topic of this fraction right here, of the alternating like that. And so if you were to continue on like that, then you would end up getting something very similar to what we're going to be talking about, which is Gregory, into our next point. So kind of going off of what we were talking about in the previous infinite series about how Broca was influenced by Leibniz and this kind of idea of this continuous fraction, the result is going to look very similar to what Gregory came up with in 1675, this idea of using the arctangent function to be able to represent a continuous series as such. So we have arctangent of x in the integers. We're going to set that equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9, and it just keeps going with the odds. And so this is what Gregory came up with, and then Leibniz decided, one day it's like, this is too complicated. I'm going to make this a little bit more simpler for my life. And so Leibniz decided to be like, hey, why don't we just set x equal to 1? When he thought that because he knew that arctangent of 1 would equal pi over 4. Kind of seeing something similar to what Bruckner was talking about in the previous infinite series, which I was talking about. And so if he knew this idea, then he was able to like, okay, well, why if we plug in 1 in for the function that Gregory came up with to get something like this? So we have, that one doesn't work. So we have arctan of 1, which really equals b pi over 4. And so let's set that equal to 1 minus anything cubed to the 5th of 1 is just going to be 1. So 1 over 3 plus 1 over 5 minus 1 over 7, and on and on and on. And so this was a very simple way Leibniz came up with using Gregory's arctangent function to be able to solve for pi. And if you were to make it more simpler, same concept, multiply 4 on both sides, so you get pi to equal to that. So it would take this 300 terms to basically estimate to 2 decimal places of pi, which actually makes it really complicated and slow to be able to get to approximating, which is very much kind of different from today when you're able to plug into a generator, which Kapua will talk about a little bit different about these awesome broskies being able to come with this awesome algorithm to get trillion digits. But way back then, this was just a way kind of general representation of showing the concept of pi without trying to write out every single decimal. And they were able to get pretty close. They were able to get approximating, like in the list back then, about 8 decimal places, so pretty good. So, so in conclusion, this is not going to be the most efficient way of calculating pi, but the concept of series and being able to converge into pi is probably the one, is the more powerful way of kind of using the ideas of arctangent and being able to combine that is probably the most powerful thing of estimating pi.
Okay, so the Chudnovsky-Broskis. This is their algorithm. It's confusing, it's long. This whole entire thing here equals 1/pi. How does it do that? It's similar to an arctan series convergence, and this is what's used for computational approximations of pi. And the two brothers, David and Gregory, worked on this. It was mainly Gregory that did it. He's like the brains of the family, even though they were both really smart. He was like genius status. Anyways, so this right here is mainly used in Python. There's an extension, I think it's Gimpy, and with that, it's able to basically approximate 100 million digits of pi in less than 10 minutes, and that's really fast. So this right here, after 4 iterations, you get 51 digits of pi, which is crazy, unbelievable. And this is one of the leading ways of approximating pi in today's days. Okay, so let's think about pi a little more. Let's see if we can find some more significance within the numbers. Let's take the square root of pi. That's 1.77245. There's nothing that comes to mind that's significant about that number, so let's try something new, something else. Let's try pi squared. That's 9.869. And that sounds a little familiar. Let's look at the standard of gravity, little g. That's 9.806 meters per second squared. We can find an equation that uses both of them together, like the equation of the period of a pendulum swing. So that equation looks a little something like this. We have the period of the pendulum swing equals 2 pi times the square root of the length of the pendulum over little g. If we make this 1/4 so that the length is 1/4 of the standard of gravity, we have something like this. The length is going to be 2.45 meters over 806. Rewrite this so that it does show the 1/4. Simplify it a little bit more to get 1/2. Take that out, and we've got pi. So if we can find pi using this equation here, maybe we can use the pendulum to approximate pi using time and a little bit of a banana. Hey guys, so we're at the pendulum now. We've made this 2.45 meters, and that is 1/4 of the standard gravity. So see if we can approximate pi. We're going to swing this, count 10 times, and hopefully we'll get it close to 3.14. Alright, so we're going to bring this back, and hopefully by the end of this we'll have approximation for the banana cream pie.
One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh. Here we got 33.58. Not too bad. What a great exploration we went through with pi, huh?
Yep. I'm exhausted.
You know, infinite series,
The Chibnowski.
the Chibnowski broskies, that theorem, swinging banana pie. I mean, boy, what do we have? What a crazy experience we've gone through. But
so much pie in so little time.
but it was a great time. And but wait, were you about to say something before?
Yeah, I was gonna ask you a little something. Do you know what the worst part about being hit in the face with pie is?
It's messy.
No. It lasts forever.
That was a good one. Because it's irrational. I got it. Well, on that note, I think we need to end it there. Thank you so much for watching. Stay tuned for more pie, because it's never ending.